All right. Good morning, everyone. Today it's a pleasure to introduce Saptarshi Roy. Saptarshi is a new postdoctoral fellow here at UT, joined with IFML and statistics and data science. He just recently, like 5 minutes ago, got his PhD from the Department of Statistics at University of Michigan, worked with Ambuj Tewari. He's interested in privacy, generative model, and high-dimensional statistics.
Thank you. Thank you for the introduction. Hi guys. So today I'm going to talk about on the computational complexity of the private high-dimensional model selection. So in particular, I'll be talking about how to select a model in a private manner in high-dimensional sparse linear regression setting. Okay, so here's the plan. So first, we'll go through some short introduction. Then we're going to talk about what is differential privacy and how to incorporate them in the context of model selection. Then we're going to talk about the best subset selection and how to inject noise to achieve differential privacy. And then we're going to talk about the computational aspect of that algorithm. In fact, we're going to show that it is efficient, provably, and then some simulations, and if time permits, then some future directions. Okay, so in a nutshell, my research lies in the intersection of high-dimensional statistics and modern ML problems, including model selection, online bandits, computational efficiency, and of course, differential privacy. So this is the paper that we're gonna discuss today. So what are the key points of the paper? So I'm gonna discuss those first. So what we did in this paper, so we considered the high-dimensional sparse linear regression setting. We opted for the exponential mechanism to select the model in a private manner, and I'm going to define what is privacy, what is exponential mechanism in the coming slides. We also showed that provably this algorithm can give you the estimate within polynomial time. So polynomial in the problem parameters. And also we showed that our algorithm achieves the best of three worlds: privacy, utility, and computation. Okay, so let's dive into details. So this is a high-dimensional linear regression model. Y is the response variable, X that is equal to X transpose beta, plus W is the noise. X is the feature, and throughout the talk, I will assume that my input data space, meaning the feature, it is bounded in sup norm. And the parameter, the signal vector beta, it is bounded in L1 norm. And beta is sparse, meaning there are S features that are actually contributing to this model that affects the response Y. Gamma star is the support. And then a very important parameter, it is defined as the beta mean. It is beta mean, which is defined as the minimum signal strength of the beta vector. And this will come again and again and again in this talk. And one standard assumption on the noise, that is the W is a sub-Gaussian noise. For example, Gaussian noise is a sub-Gaussian noise. Bounded noise is also sub-Gaussian noise. Bounded noise with mean zero is a sub-Gaussian noise. Okay, so now what is the goal here? The goal is, of course, to identify the true support gamma star, but there is a catch. We have to maintain the privacy of the data. Now, under the non-private setting, there has been plethora of works, Lasso, AIC, BIC, and they have all shown whenever beta mean is large enough, meaning if it is at least square root log p over n, all of these methods works pretty well. They can achieve model consistency, meaning they can identify the gamma star with very, very, very high probability is approaching to 1. Now, in the privacy framework, there have been many works in empirical risk minimization setting, in estimation, improving private rate for the consistency of estimation. But throughout the past 10 years, there has been only 3 works on private model selection. So Kiefer, Thakur, Smith, and Lee. By the way, The last paper is by two very prominent computer scientists, by Adam Smith and Dork. And they were the first to propose the notion of differential privacy here. Okay, now these three works on private model selection, they have their own limitations. First of all, the Kiefer et al., they propose two types of algorithm. One is the ERM-based, or one is leveraging the ERM-based framework, and another is resample and aggregate framework. For the ERM-based framework, they only try to select a model which sort of tries to minimize the excess risk, and that is not really the model selection. And they also assume some kind of bounded loss function. And the most disturbing part is that they do not say anything about the computation complexity of the algorithm. And in fact, the first algorithm that they propose is NP-hard, meaning you're basically searching over a search space which is exponentially large. The second one, the resample and aggregate method, that is an efficient method, meaning that you can do it under polynomial time, but the beta mean condition is very stringent. In fact, you can see the condition is at least square root n times larger than the optimal condition in private, not in a non-private setting. Now, a year later, Thakur and Smith came up with a better algorithm, leveraging the power of lasso. But the point is that their utility guarantee is very bad, meaning the recovery probability does not approach 1 as your sample size grows to infinity. And that is not something you desire. And also their beta mean condition is better, but still much, much bigger than the square root s log p over n. And at the very end, Lee et al. Proposed a noisy max algorithm, which is again an exponential search algorithm. You cannot implement that in real life. However, their beta mean condition is good. So this table perfectly summarizes the pros and cons of all the papers and the works. So Kiefer et al., they have two algorithms. The first one, the runtime is exponential, and they do not even talk about the beta mean condition and the failure probability. But the second condition needs very stringent beta mean condition. Coming to Thakur and Smith, their beta mean condition is somewhat better, but their failure probability does not converge to 0. So that's the negative point of their work. So Lee et al., they proposed the exponential mechanism again. Their beta mean condition is okay, but their runtime is exponential. So in our paper, we first also proposed the exponential mechanism. And note that the beta mean condition is strictly better in our case. The failure probability does go to 0, but the runtime is exponential. So to circumvent this issue, we sort of propose an approximate exponential mechanism that leverages the power of MCMC, Markov chain Monte Carlo, that has exactly the same beta mean condition. Failure probability does go to 0, but the plus point is the runtime is now polynomial. You can actually implement that. Okay, so if you look at the years, it has been 6 years. And there was no work in private model selection, which achieves the best of 3 worlds, utility, privacy, and computation. And that sort of made us curious what could be the plausible reason. So we realized you sort of need the blending of 3 types of theorems or 3 types of results. You need the knowledge of high dimension statistics, you need the knowledge of privacy, and you also need the knowledge of computational theory, which in this case is the Markov chain mixing time. And blending these 3 are not turned out to be very non-trivial. Okay. So again, the contribution of the work. So what did we? So again, it is enjoying the best of 3 worlds: privacy, utility, and computation. And we show that under high privacy regime, meaning when you are actually concerned about the privacy, you just need your beta mean condition to be larger than square root s log p over n. So there, it is almost the optimal rate, but with a factor of square root s. But in low privacy regime, you get back the exact optimal rate. So there is no compromise there. So meaning there is a phase transition in terms of the requirement under privacy. And also, we provably show that this algorithm converges really, really fast. In fact, it is polynomial in the problem parameters. And the approximate algorithm actually achieves approximately. Okay. So now it's time to introduce the notion of differential privacy. So let's say I have a mechanism, M, and I have some data points, x1, x2, x3, x4, and there is some user. So what is happening? So the mechanism takes the x1, x2, x3, x4 as input and spits out some statistics. It could be classified, it could be mean, whatever, and it shows it to the user. Now it may happen the user is a bad guy. He's an attacker. But what is the problem in that case? So consider this example. Let's say x1, x2, x3, x4 are the individual incomes. And that's a very private information. You don't want to divulge any kind of information about income. And let's say M is my mean operator. So I pass this data set through the mean operator, show it to the attacker. And let's say I pass another data set D prime, which is slightly different. In fact, it is different in the sense that it is different in one input. And I pass that data through the mechanism and show that to the attacker. So the attacker has now two outputs, MD and MD prime, and he or she can take the difference between them. And if it turns out that the difference is very large, he can immediately infer that X4, meaning the X4 in this slide, this orange guy was very rich. He has a very high income. And this is basically leveraging the fact that mean is very non-robust statistics. So in a way, this mean operator is divulging some information about the income. And we need to remedy this. So the usual trick is to you have to do something that can blur the information in the output. You have to inject some kind of noise in your mechanism, in your learning mechanism. And what is the point of that? So you have to inject noise in a way so that the final output, irrespective of the small changes in the data set, it will give you the similar looking output. And when the attacker sees that, he or she gets confused. He cannot infer whether this output happened due to D or the D prime, meaning I cannot predict any change in the data set. So the idea is it has to output a similar looking probability distribution on the output space. Yes.
Yeah, so there are two ways to do it. Right? One is to put noise to the income of every person.
Yes.
And the other one is to first compute the mean without any noise.
Yes.
And then add noise to that mean.
Yes.
Are they equivalent or are they different?
They're equivalent in the sense that if you want to achieve privacy, yes, they do the same thing.
Right.
But if you think of it from the point of view of utility, the first one, meaning if you add noise to each of the individuals, is very bad because you are adding too much noise, and that will burn the data itself, and you cannot gain any information from the statistics. Yeah. So the first one will suffer from very low accuracy.
So are you going to talk about mainly the second type of thing?
Yes, mainly the second type of thing. So I think that injecting noise to the input gives you local privacy. I'm not going to talk about the local privacy. It's the global DB. Okay, so one very small fact. Utility on itself is very easy to achieve because if you give me a data, I run some algorithm that has high utility, right? Privacy itself is also very easy to achieve. You give me the data, I burn the data. No one gets to see anything and it's private. Balancing these two becomes hard. And in fact, there are works which shows that achieving these two simultaneously is very hard in some cases. Okay, so I said that you have to to achieve differential privacy, you have to output probability distribution, which are close. Now, close in what sense? So this is the definition, the mathematical definition of differential privacy proposed by Adam Smith, Cynthia Dork, that group. So pick two non-negative number. In fact, epsilon has to be positive, delta can be non-negative. So 2 parameters, epsilon and delta. And we say that M, a randomized algorithm, by its definition, a differentially private algorithm has to be randomized. A randomized algorithm satisfies epsilon delta dp if it satisfies this inequality. So if you stare at this inequality long enough, you will realize that it is sort of saying these 2 probability measures under when you start from D dataset D and you start from a neighboring dataset D prime, the final output measure, they are close in the hockey stick divergence. So what is hockey stick divergence? So you basically define this function f epsilon t, and if you plot the graph, it looks like hockey stick. That's why hockey stick. And you just take the expectation with respect to that f epsilon function, and that gives you the hockey stick divergence. So what differential privacy is saying, if you start from D and D prime, the final output measures, those two have to be closed in the hockey stick divergence. And how close? Delta close. So meaning your 2 distributions are almost similar looking. And what does that mean is that irrespective of the change in the dataset D, even by a single point, the output doesn't change very much. Okay, and another very key point is that the differential privacy is the condition of the algorithm, an algorithm only. It is not dependent on the data set, meaning if you look at the definition, it says that this inequality has to hold for every pair of neighboring data set. So it doesn't matter what type of data set you are inputting in the algorithm, it has to hold, to maintain differential privacy, it has to abide by this inequality. Meaning it is solely the property of the algorithm itself. Okay, now what are the strategies to achieve this differential privacy? Let's say I have an algorithm F, which takes n data points as input and spits out a real number. So first we have to ask, how much does it change if I change 1 data point in the input data set? And in fact, I have to go for the worst case sensitivity, and that is defined by the delta F here. So it is taking the supremum over D and D prime that are neighbors, and you're basically measuring the change. If you have that, you just add a Laplace noise that scales with del F, and you can show that this preserves the epsilon comma 0 differential privacy. And this is called the pure DP. And there's also something called the Gaussian mechanism, and you can guess from the name that Z in that case has to be appropriate Gaussian noise. So in this way, you can achieve approximate differential privacy and pure differential privacy. And there is a third algorithm, which is very general. It is called the exponential mechanism. So for the exponent, yes. Yeah. So exponential mechanism. So what is exponential mechanism? So to even begin to talk about the exponential mechanism, you need something called the utility function. So utility function is a function that takes a state space S and the input data, so X power n, and spits out a real number. And again, you need to ask what is the global sensitivity of that utility function. So del U basically measures that. And they do something very smart. They construct this discrete probability distribution. Probability MED equal to F, that is proportional to the exponential epsilon times U alpha D and over del U. So epsilon is the privacy parameter, how much privacy you want. So they showed that if you can sample, if you can sample from this distribution, then the sample itself enjoys 2 epsilon comma 0 differential privacy. And in fact, if your utility function is monotone in the sense that it behaves monotonically with respect to the addition or deletion of a new data point into your input data set, then you can actually say something more. It becomes epsilon comma 0 differential privacy. So you can shave off the 2 factor here. Okay, so this is the mechanism that we're going to use now. Yes.
There is only rules for a discrete state.
For now, yes. Yes. I think it also does hold for continuous space. I guess it also holds for continuous state space, because in that case, your scaling factor will be just integration over the state space.
And what will that probability be?
It would be density. It would be density. Yeah, this slide is purely for discrete case, but in the continuous case, it would be density.
So I understand the thing. So, let's say n is the mean,
Yeah.
and then alpha is like, proposed answer for what the mean should be, and then the utility is how far they differ from each other.
Yes.
Okay, so, in that case, does this last point hold
The last point,
of this being data monotone?
the data monotone, no. For mean, it does not hold.
Okay, so for mean, you cannot apply it yet.
No, mean you can apply. You will just get 2 epsilon comma 0 dp. I'm saying if it is further data monotone, you can shave off the 2 factor. It is just becomes epsilon comma 0 dp. So it's just an additional result. Okay, now we're going to use this exponential mechanism trick in the best subset selection. So first of all, what is even best subset selection? So recall the linear model. So what you are trying to do, we are trying to find the best model which sort of minimizes the L2 error rate over all possible models of size at most S hat. So S hat is a tuning parameter here. And in fact, you can rearrange, do some algebra to get the second line, which is basically solving for a gamma hat S hat, which is trying to minimize the RSS, the residual sum of square, in the linear model over all gamma of size S hat. And phi gamma in this case is basically the projection matrix onto the feature space restricted to the model gamma. And people have shown that there is something called the M star S, which is called a margin quantity. And what it shows that if this M star S is large enough, meaning that sigma square log p over n, again, that optimal rate is coming, log p over n, then best subset selection can actually identify the true model here. And also this M star is sort of within a constant factor of the beta mean square, the minimum signal strength. So any condition on M star S is basically demanding that beta mean square has to be large. So you can read it as if beta mean square is larger than sigma square log p over n, then best subset selection can achieve model consistency. But this is for non-private case. So how do we achieve privacy? So here is the trick. So first of all, we need to ask what is the utility function, so which is UK in this case. So if you look at the definition of UK, it is, so basically you are trying to maximize the utility. So that's why there is a negative sign. So minimizing loss means you are trying to maximize the negative loss. So it is basically same as the best subset selection scheme. But the only difference is that you are adding an extra constraint, extra L1 constraint here. So minimizing over theta such that theta is within the L1 ball. And then you're trying to minimize the L2 square error rate. So why this L1 constraint is needed? To make the utility function robust. And what it does, it gives us the worst case sensitivity of the utility function. And in turn, that will give us the worst case DP guarantee. And I just want to point out, we do not need any linear model assumption in this case, like till now, to do anything about the privacy. And that is very important. You cannot assume anything about the model when you are showing something is private, because one can ask, well, you are actually using the properties of the model to guarantee something is private. What if the data does not come from that model? So that's why you have to be very careful when you have to say something is worst case DP. So people are really, really concerned about it has to be DP irrespective of any type of data set. Yes.
What is the K in the UK?
K is the L1 ball radius. So it's a tuning parameter.
It's a tuning parameter.
Yes. So your algorithm takes the k as the input also.
Question.
Yes.
So in, for the mean, you're keeping the samples private.
Yes.
But here you have y, x, and y and x. What are you keeping private? X
I'm keeping
from the attacker.
I'm keeping the loss private actually. So this y minus x gamma theta square, this is being blurred here. We are injecting noise to this guy. And
okay, so the information given to the attacker
yes,
is some value of the loss. Like
the information given to the attacker, no, the attacker can only see the output of the algorithm. So meaning
what is the output?
the gamma, the model.
The gamma.
Yes.
So you can only see the model.
Yeah, or output model.
Right.
Yeah.
And what the attacker should not be able to guess is
If there is, let's say, any sensitive information in the data, attacker should not be able to say, well, this particular individual has that property.
they should not be able to figure out the x.
Yes. X is the input. Yeah. X and Y something.
X and y.
Yeah.
So you want to keep x and y private while still revealing gamma.
Yes. Yeah. Any questions?
I have a question about the sparsity constraint that you showed.
Yeah.
In the past. Is this dependent then on the sparsity of the data?
Yes. So for now, our algorithm is not sparsity agnostic. You need the knowledge of S.
Okay.
Yeah.
All right, thank you.
Because I'm going to search over all the models which has that sparsity S. So it is using that information.
Okay. Thank you.
Okay. So I guess the setting is clear. The strategy is clear. And let's say some assumptions that the response are bounded, and I've already told that the feature is also bounded in the SUPNOR. You can actually give a deterministic worst case upper bound to the sensitivity, which is r plus x max k squared. And let's call it delta k. And if you just substitute your delta of uk by the delta k, and let's say you can also sample from that distribution, which you cannot in practice, but let's assume that you can sample from the distribution, your model estimate, meaning the output of the algorithm, will satisfy epsilon comma 0 dp. Why epsilon comma 0? Because you can also show the utility function in this case is data monotone. And that will help you to shave off that 2-factor. Yeah, again, we are not assuming linear model yet. Now, I need to say something about the utility. It's private, but how good is that estimate? So to state something about the utility, we need further assumptions. So beta is already bounded, and we need something called the sparse eigenvalue condition, which basically says that if you look at the gram matrix restricted to the gamma blocks, they have essentially positive curvature. And also we assume that the sparsity is bounded by n over log p, a little bit less than the sample size. And under that condition, what you have is, if you choose your tuning parameter k judicially, and your m star s, which really means that if your signal strength is large enough, and look at the rate, it is log p over n. So again, it is the optimal rate. And also there is something called the max of 1 and delta k over epsilon sigma square. This factor, this max factor, will give you the phase transition. So if your signal strength is large enough, this pi gamma star, so recall that pi is basically this distribution, pi gamma. This will put high mass on the actual gamma star. So it will put 1 minus p square mass on the actual gamma star. And few words about the max thing here. When your epsilon is very large, delta k over sigma square, meaning you are in the low privacy regime, you get back the optimal rate for the which is same as the non-private model selection. And if your epsilon is small, meaning you are actually concerned about privacy, high privacy regime, you pay with a factor of s over epsilon, which is not so bad if your sparsity is small. So this is the phase transition I was talking about. And you can imagine, you can guess why there is a S over epsilon, because delta K, you can see that K is like square root S here, and your delta K scales as K squared, and that's why S is coming. Okay, so this is the phase transition, and that's good. So if you can construct this distribution, you achieve epsilon comma 0 dp, but the point is that you cannot sample from that distribution because you're again you're basically searching over P choose S many candidates, and you cannot do that yet if your P is very large. So one way to solve this, you sort of try to approximately sample from that target distribution. And how do we do that? We have to come up with a very clever Metropolis-Hastings scheme that will gradually go towards the target distribution. So a few words about what is Metropolis-Hastings. So basically, if I'm in a current state, you have to sort of construct a neighborhood, you have a proposal distribution, and once you choose the new state, you have to toss a coin. If it is heads, you go to that space, go to that state, otherwise you stay put. And the toss a coin, it has the probability R gamma. That's the rejection probability of the Metropolis-Hastings. And this is very important. This makes the Metropolis-Hastings chains balanced, meaning reversible. The three important points. So this chain that you have constructed on the state space, it has three key properties. It is finite state, it is irreducible, and it's also ergodic. Moreover, it is balanced due to as you have chosen R gamma like this, it is balanced. And all of these three properties makes the chain very unique in the sense that the stationary distribution of this Metropolis-Hastings chain is unique. And in fact, it is the target distribution. So it is safe to say that if I run this Markov chain, I'll get closer to my target distribution. So uniqueness is very important here. Otherwise, I may end up with some other pi. And the big question is, how fast does this MCMC chain converge? So the way we measure the time, like how many times we have to run the MCMC chain, by simply saying, I want to stop whenever my probability distribution at the tth iterate of the MCMC chain is eta close to my target distribution in total variation distance. So if I'm running the chain, I want to measure that the distribution at the tth time point is like, say, eta close, and then I'm going to stop. And in fact, this tau eta measures the worst case eta closeness, meaning no matter where you start your chain, you eventually end up in the eta neighborhood of your target distribution. So tau eta is very worst case mixing time. And eta is the mixing quantity. How close do you want to be to your target distribution? You can show that once the chain has mixed, this gamma tau eta, that is the model estimate, it is epsilon delta dp, not pure dp anymore, but approximate, where delta is eta times 1 over e power epsilon. So if your eta is small, mixing quantity is small, this epsilon delta dp guarantee is a pretty good guarantee. But again, the big question lies how fast you are mixing your chain. So for that, you have to first sort of come up with a clever scheme. So we come up with a double swap scheme, meaning that if you're in a state, let's say gamma is a state of the MCMC chain, you can think of it as a bit vector, a vector of 1 and zeros. 1 signifies the active features and 0 signifies the non-active features. What I do, we choose one of the coordinates from the ones, switch it off, one of the coordinates from the zeros, switch it on. This is called a double swap. And this also makes the chain irreducible, positive recurrent, ergodic, whatever. And the thing you have to look is the probability transition kernel, PMH, of the Metropolis-Hastings. And what you want to analyze is the gap of that transition kernel. So you want to show, so first of all, the lambda max is basically the max of the highest eigenvalue and the second lowest eigenvalue of the transition kernel. And 1 minus lambda max is the gap. If you can show this gap is very large, you can show the mixing time of that corresponding Markov chain is very small. And that is a good thing. That's what you want to show. Unfortunately, it is not very easy to analyze. So you have to go there in a sort of roundabout way. So there is a beautiful theory by one computer scientist named Sinclair. That person developed a very beautiful theory how to analyze this gap. And in fact, you have to come up with a conductance. So you have to see the Markov chain from a graph point of view, on a network point of view, and you have to sort of analyze the conductance of that graph. So think of conductance as the measurement, how probability or information is flowing smoothly through the network. It is same as the conductance as physics. So you have a conductor, you want to measure how smoothly an electron is moving through the conductor, right? And that is conductance. So in this case, how smoothly information is flowing within the graph from one section to another section. So the goal is you have to sort of quantify what is the conductance of a graph, and you have to give a lower bound to it. If you can give a lower bound to the gap, to the conductance, it will give you a lower bound to the gap, and in turn, it will give you an upper bound on the mixing time. So here's a more intuition about the conductance parameter. So let's say you have a graph like this. It has two sections. So one is S and S prime, and you can see there are very few connections between them. So phi sort of measures the flow of the probability of the information from S to S prime. And in this case, if your connection is low, the conductance is low. And if you increase your connectivity between S and S prime, your conductance increases, meaning the flow is flowing more smoothly here. Yes.
But that's only true for unweighted bits, right?
I think here it is also weighted because yeah, we have to look at the weighted graph here, where this is the weight.
I'm just thinking about the basis of Srivastava and Spielman's approach to cutting graphs.
Yeah.
Minimum
Yeah, I think the original theory is
based
for
on this
yeah.
same notion,
Yeah.
but you increase the weight, therefore you increase the conductance. It's kind of analogous to increasing the size of the wire.
Yeah, yeah.
So weighting in their situation allows you to get around that. So I guess that's what there seems to be a tension between what they propose versus what's being talked about here. In the weighted sense.
Yes. I guess I'm just I think this definition is for the unweighted graph. I'm not very precise here about the weighted graph situation.
Okay.
Yeah.
Okay, thank you.
Yeah, I just wanted to give some intuition how the probability is.
Got it.
I think you're right. Yeah.
Thank you.
Okay, as I was saying, if the connectivity increases, the flow also becomes smoother in some sense. Unfortunately, this is also hard to show. So what you have to do, you have to sort of construct something called a canonical path through the graphs. And you have to show those paths are not so congested, meaning that literally, if you imagine a traffic flow through those paths, you have to show that the most congested path in that network is not so congested. And that will actually show that the flow is smoother, right? So that's what you show here. So rho is something called the congestion parameter. And we are able to calculate this rho, and that actually gives a lower bound on the phi, and that in turn gives us upper bound on the mixing time. But there is a catch. As MCMC is trying to search locally, so given a state, I'm trying to decide where is my next best local move. So it's a local search algorithm. We need one more assumption. So this assumption basically says that my spurious features are not so correlated with the features in the true model. So xj here is one of the true features, and xk is one of the spurious features. Those are not correlated. I mean, they are correlated, but not too correlated. So if you have that will help us to take the decision where does my next best local move lies. It will show me the correct direction. So if you have this, you can show that your MCMC algorithm actually converges under the same beta mean condition. It converges really fast. In fact, polynomially, you can see it is polynomial in P, the sparsity, and the sample size N. And in fact, you cannot get away with the n times p factor. Why? Because the matrix itself is n cross p. So you need np or np computation to read the matrix itself. We are saying you just need a little bit more, a square more. Okay, so this proves the polynomial mixing time of the chain. And in fact, if you stop at t, where t is much larger than the mixing time, it will give you that the pi t gamma star is the true model that is at least 1 minus eta minus p squared. And now you can choose your eta. Let's say I choose my eta to be p, 1 over p squared. It will give me that pi t gamma star is actually very high. And my mixing time is np a square log p, which is still polynomial in the problem parameters. Okay, so a few simulations. So it's a very small example. So let's say n is 900, p is 2000, sparsity is 4, and all of the entries of the design matrix coming from uniform minus 1. So two types of signal. One is with the S factor. I call it the strong signal, and the weak signal, which is just the square root log p over. And the noise is coming from minus 0.1 uniform. So this picture is only for the strong signal. And we are measuring the F. So F is sort of an in-sample R square statistics here. So I'm starting the chain randomly. And I'm proceeding through the chain, and it shows that it's trying to approach this red line. Now, what is this red line? Red line is the R square statistics of the optimal gamma. So there are actually two lines here. Blue line is the F statistics of the true gamma star, and the red line is the F statistics of the model that you will get from the actual BSS. So here we cannot run the actual BSS because it's NP hard, but there are some approximate methods. So you can also calculate the F gamma, and what this simulation shows is that if you run the MCMC chain slowly, the chain will approach towards the optimal model. Here. And these three pictures are for different levels of epsilon equal to 3, 5, and 10. And these are the strong signal case. And in fact, to measure the quality of the estimated model, like how much does it capture, how much it can identify the true model, we compare the F score of the estimated model. And you can see that in the strong signal case, it is quickly approaching 1 as epsilon increases, but it is really struggling when there is weak signal. And it is expected, right? The signal is weak and you're injecting noise to make it harder. So it will take much, much larger epsilon to actually go to 1, to actually give you an F score of 1. So F score 1 means it is a perfect identification of the true model. Okay. So that's all for the simulation, and there are a few feature directions that we are thinking of. That, as I said, the current algorithm is not sparsity agnostic. We need the knowledge of sparsity. So there is definitely a space where you can make this algorithm sparsity agnostic. We don't want to use the knowledge of sparsity. Also, I'm not sure whether this beta mean greater than or equal to S log P over N is necessary or not, meaning whether this S factor is necessary or not. Can we get away with this S factor? If it is true that we can get away with this, it would be fantastic, right? That means it's basically saying you need essentially the same amount of signal as the non-private case. So that's one research direction. The other is MCMC algorithms are in general pretty slow for large data set. But there is a framework called the mixed integer optimization, which sort of tries to solve this base subsolution problem via a MIO framework. The point is, it is not clear how to incorporate the differential privacy or inject noise in that framework. So it would be very nice if one can come up with an easy way to blend the DP framework and the MIO to give us some user-friendly algorithm. And the point is that MIOs are very fast in solving these L0 constrained problems. And of course, computational complexity is another issue. What about that? And lastly, I want to acknowledge my collaborators here. So Zewa, who is a master's student back in UMich, and my advisor, Professor Ambuj. And with that, I would like to conclude my talk, and I'd be happy to take any questions. Yeah.
In general, the exponential mechanism is not efficiently implementable, right? What's special about this problem that kind of created
The linear structure.
Yeah.
The linear
so
structure.
is it kind of typically employed for such?
I think you can also do it for exponential families because you have a particular form. You can play with the algebra and you can show certain things there. But the moment the model becomes very hard, it becomes hard to analyze the congestion parameter or the graph network itself. But at least in this case, it is not that hard. Yes.
Okay, so I have a naive algorithm.
Yes.
And so I'm just wondering if it'll have like bad privacy. So if I'm the mechanism, I'm supposed to reveal a support set. Now I know the true support set, right? So let me just flip a coin for every coordinate. And if it comes up heads, just leave it as it is. And if it comes up tails, then change its state somehow, right? And I can choose the property of heads and tails, the positive level remains about the same. And I'll give you a noisy support. Okay, so this is like this is much, like you're doing Metropolis-Hastings to find the right distribution.
Yes.
Right? This is a really bad. So is this really bad for privacy?
I think so. You know the gamma star you are saying.
The gamma star, right? And then I'm going to give you like a gamma hat, which is a noisy version.
So basically, you
Metropolis-Hastings, on the Metropolis-Hastings was just a way to get to gamma hat from gamma.
yes,
star, right?
yeah.
So what if I get to it in this stupid way? Like
I think the utility will be very bad because you're randomly flipping the bits.
right, but with low probability, yeah. Yes, I'm randomly flipping them with some probability that keeps the overall sparsity about the same, but changes the support set a little bit. The utility will be bad. I mean, I'm just asking.
Utility, I think it will be bad unless. Let me think. Let me think a bit more. Actually, I'm confused. How do you know the gamma star?
I thought the mechanism first knows the true gamma star, then adds.
No, the mechanism does not know the gamma star. You just give the y, x, and the k parameter. That's it. It does not know the gamma star.
But it can find it.
Sorry?
It's pretty easy to find the gamma star. So the gamma star is the best sparse vector for.
Yeah, but you cannot do that. Then otherwise you'll be breaching privacy. You have to know so the moment you are saying that you have to spit out the gammas or estimate of the gamma star, you have to do that in a private way.
Let's take it out.
Oh. Okay. Yes.
One question. Here you assume a linear model, and that's crucial for your analysis.
Yes.
Right? What if you can assume? I would say maybe another reason why people sort of have not worked as hard is that the linearity is weak, as far as a strong assumption.
Yeah.
What if your model is not linear, the distribution is not linear, but yet you system fitting a linear model, which is what people do in practice all the time. So now your target parameter, the beta will be the best linear approximation to the full model. And then sparsity, you have to reasonable sparsity in that context.
Yes.
You have a sense of how, what kind of theoretical result you can now guarantee in this sort of model agnostic framework. You still get something sparse, you still essentially give support.
Yeah, so essentially you are asking about model misspecification, right? So your model is misspecified to begin with.
Yeah.
And you're trying to do this algorithm, right?
But there exists a parameter, even if it's model specified, there is a parameter that, capture the.
Right. Let's say through some Fourier basis or what not.
Yeah.
I think that this result will give